Okay, here we're on section 9.2 on matrix solutions of linear equations. So our objectives are representing systems of linear equations with matrices, relating matrices and social networks, applying Gauss-Jordan elimination, and using technology to solve systems of linear equations. Now, representing systems of linear equations with matrices. So a matrix is a rectangular array of numbers, and each number in the matrix is called an element. Now, matrices can be used to represent a system of linear equations. Now, a vertical line is positioned in the matrix where the equal sign occurs in the system. So that equal sign is right here. So this is our left side, and this is our right side of the equation. Now, this is a matrix that has a dimension of 3 rows, 4 columns, so 3 by 4. Okay. Now, when we do this, this first column is going to usually be our x's, this is going to be our y's, this is going to be z, and again, that's equal, and this is just going to be our constant, so whatever our constant value is. Okay. And so this value here, it says 3x minus y plus 2z equals 7. Here it's x minus 2y plus z equals 0, and 2x plus 5y minus 7z equals a negative 9. So we could rewrite that as a system of equations, or this is going to be our matrix for that solution. Now this going down this way is called our matrix diagonal, and we'll be using that to do the Gauss-Jordan elimination in a little bit. All right, so what we want to do is represent each linear system with an augmented matrix, which is what this is called. This is called an augmented matrix, and we're going to state the dimension of the matrix. So we have a 2 by 2 system and a 3 by 3 system, and so what we have is it's going to end up being a 2, because this is, two equations, two unknowns, 2 by 3, because we have the extra column with our equals, whatever our constants are. And this is going to be a 3 by 4 because, again, that constant column. Okay. So we write it, we just put our constants here. So we have 1, then minus 5 equals 6. So that's our first row. And then 8, 3, and 12, that's going to be our second row. Now this one again, like I said, is going to be 3 by 4, and it's going to be 2, 5 minus 2, 4, and 1, 4 minus 2, 6, 2, 1, 9. And now notice we have a 0 here. So if it's nothing there, we have to plug in a 0. So that's going to be a key difference here is we don't usually put in a 0 z, but in the matrix, we actually have to put that value in as a 0. All right, so Gauss-Jordan elimination is going to be how we actually solve our system of equations in the matrix form. And so it's a convenient matrix form for representing a system of linear equations, and it's in reduced row echelon form. Now, if an augmented matrix representing a linear system is in reduced row echelon form, we can determine the solutions very easily. Okay, so looking at this, these both are systems of equations again, and we want to find the solution. Well, if we look at this, this is in row reduced echelon form. So we just have 1 down the diagonals, our main diagonal, and zeros everywhere else. And same thing here, 1 down the diagonal, zeros everywhere else. And so what that means is, again, if we remember, that's x, that's y, that's z. So it says x is 4, y is minus 2, and z is 1. Here we have x and y only, so x is minus 2, y is 3. And so that is going to be our solution. So once we get it to this format, we have our solutions. And so again, 4 minus 2, 1, that's our solution. And here, it's going to be minus 2, 3. And that's going to be our solution. And again, we just say, this is x comma y comma z. This is just x comma y. And that's what we have from here. All right, let's stop there and we'll come back for some more.